Greetings everyone and welcome back to the bench. Well, I need to produce some square waves with fast rising edges for the amplifier project. I want to be able to test this amplifier. So I'm going to take a look at doing that in this video. I must apologize for not having a lot of videos up lately. Besides the Cordell audio book review I did in the last video a few days ago, it's been June 13th since I put up the last electronics video. The reason for that is just been busy with work. Normally it slows down in the summer a little bit, but it's been pretty intense lately. And I'm grateful for having a good amount of work to keep me busy. Not a lot of time for playtime, so that's what's going on. There's other personal things in my life that's keeping me off the YouTube videos, so some things good, some things bad, but I won't bore you with my personal life situation. So I need to generate some fast rising square waves to test this amplifier. And remember from the last video I was struggling with getting rid of the oscillation, and get this thing powered up in the next video and begin some more testing on it. But like I said, I need to generate some square waves. Now I was reading Rod Elliott's site. He has a very nice site, Elliott Sound Products. If you just Google that, you'll find the site. It has a lot of information on audio electronics. He says you don't really need square waves with fast rising edges because the amplifier will never see music with such waveforms that have such a fast slew rate. Yeah, and that does make sense. That's true. But I think if you really want to flesh out any problems with the amplifier, you want to feed it a signal with a very fast edge, because in the real world, an amplifier with several stages, doesn't matter what type of amplifier, it's a tube amp or solid state, for example. There's going to be some delay in the amplifier response, and the amplifier might show issues with the waveform that has fast rising or falling edges. So this video I'm pretty much going to concentrate on talking about generating square waves with fast edges. At least as fast as I can make them here on my bench. Now there's a lot of ways of creating square waves. One way you can use those digital logic chips like the 7400 series or stuff like that. One way is using a hex inverter, and you feed that signal back using a resistor and capacitor to set a time constant, and you can generate square waves that way. And I played around with it and really wasn't happy with what I was getting. I think I could do better. So what I'm down to now is using a microcontroller here to generate square waves, and using my function generator here. This is the inexpensive Feel-Tech. You can feel the quality of this Feel-Tech arbitrary signal generator here, and compare the two, see which one I can use for testing the amplifier. So I need to set up the oscilloscope properly. I removed this ground lead alligator clip. So I just have the tip here and the ground ring. I set the probe for 10x mode. And right here is the trimmer cap, and I've already adjusted that. And to adjust that, there's these points here, these little test points on the oscilloscope, and it puts out a 1 kilohertz square wave. So if I put the tip on there, you can see we get a nice looking 1 kilohertz square wave. And adjusting that trimmer cap cancels out the effects of the probe lead, so you don't get any overshoot or anything like that. So as I decrease the time per division, you can see it's a nice looking waveform. I keep turning that up. You can start to see the rising edge there is not so straight anymore, is it? Now turn this all the way up to the limit of the oscilloscope. And it looks like just a horizontal line now, so it's not a particularly fast edge, is it? First off, we'll take a look at generating square waves using the microcontroller. So it's just a basic circuit here. Ignore this stuff, it's not part of the circuit. We have the 4.5 volt power supply, some support components, potentiometer used to adjust the output level. Here's the schematic. So the microcontroller I'm using is a pickaxe chip. It's really a 12F683, but it has the pickaxe bootloader put onto it by the friendly people at Pickaxe. Why am I using a pickaxe chip and not something else? Well, several years ago on my old channel, I think it was back in 2010 or something, a guy sent me some of these chips, and that's the first thing I've learned on. Well, I'd like to learn assembler and maybe learn on some chips how to program them, but for now I'm just using pickaxe. So yeah, these are the support components. That's just a supply bypass capacitor, and these resistors are connected in this way to keep the chip in run mode. Plus I can hook some wires up to the serial port on the computer, connect one here, and then one to ground, and program the chip. I can do it right on the board. I don't have to use a special programming board. But the main thing I'm concerned with is pin 5 here. This pin has several functions, and one of the functions is a pulse width modulated output. So with one line of code, I can turn that pulse width modulated output function on, and by putting some numbers in, I can set the frequency and the duty cycle. And the PWM is separate from the microcontroller circuitry in here. Well, I mean, it's all on one chip, but it's separate from the microcontroller in that you can go off and do other functions and, wait for input and things like that, and it won't affect the PWM output. It'll keep running at whatever frequency and duty cycle that you set. And I have a potentiometer here. Allows me to adjust the amplitude of the square wave output. So let me get the camera pointed at the scope and we'll take a look at its output. Okay, now you're looking at the output of the microcontroller, and it's right at 10 kilohertz. Adjusting the potentiometer, I can move the level up and down. Looks like there's significant overshoot. Let's look at that closer. Yeah, it does overshoot a little bit. And look at this here. If you remember when I was testing from the scope's square wave output, at the fastest horizontal time setting, it was almost a horizontal line. So you can see that this is way faster. This chip is way faster. Let me adjust the trigger so I can see the rising and falling edge at the same time. So yeah, you can see there's some overshoot going on there. And that is pretty fast. So what I'm going to do is take these little ceramic capacitors. It's a little 33 picofarad NPO type cap, and put it across the output. See if I can clean up that overshoot a little bit. Now that helped quite a bit. There's still some on the bottom here, but it's much reduced. I'm going to try a 47 picofarad, see if that's any better. And it's not much better. It's slowing the signal down somewhat. Let me go back to the other one. well, first, here it is without any capacitor. You can see the rising and falling edge is very fast. And I'll go back to the 33, if I can find it here. Cannot read these tiny numbers. I would say the 33 picofarad is the best. Of course, it impacts the slew rate the least. It corrects the overshoot hump on the top, but there's still a little bit on the bottom, but you know, I think I can live with that. So it's all the way down now that we can see the square waves. Of course, it looks like a box because I'm triggering on the rising and falling edges. So what I want to do now is take a look at the field tech, see what it looks like. Okay, I have the field tech set up on square waves, 10 kilohertz. Now its internal impedance is 50 ohms. It has two 100 ohm resistors in parallel, so because I have quite a bit of lead length on here, I've also terminated at its output with a couple 100 ohm resistors, so it's 50 ohms in parallel, or 100 ohms in parallel for 50 ohms. So hopefully it cleans up some of the effects of the leads on the output of the function generator. And here's what we're getting. So I turn that up. And that's looking pretty good. Well, I don't think it's as fast. There's a little bit of ringing. There's no overshoot or anything. Maybe if I get my fingers off there. Nope. My fingers touching it was not creating that problem. So there's a bit of ringing. So let's turn this. This is my scope's maximum. Let me go back to the function, or the microcontroller. And the microcontroller is a little faster, I think. Let's turn that right here. So here's the microcontroller. I'll jump over to the field tech. It's not too bad, really. I might have the amplitudes off a bit. Yeah, they're pretty close. So actually the field tech is not as bad as I thought. I remember in another video I kind of discounted it for use because I was getting better results, but it's actually not too bad. It does have a little bit of ringing, as I say, and just a wee bit slower than the output of the microcontroller. Yeah, the microcontroller is a little better. I'm just getting that, if I can get that to stay up there, I'm just getting that little notch, that little overshoot on the bottom there. Let me adjust this. Of course, at the input level of the amplifier, the signal would be running a little bit lower, so that is actually worsened. The output impedance of the microcontroller is actually higher. I'm using a 200 ohm potentiometer. The reason for that is I'm limited with the current on the output of the microcontroller. So I can't use too low a value without impacting the signal level as much. Of course, the field tech with its 50 ohm output impedance might actually be better in that case. You know, at that signal level, maybe I should switch back to the 47 picofarad cap, see if that's better. Yeah, I think I'm going to run with that because, you know, this is more of the signal level that's going to go into the amplifier. And that's even better. Still getting that bump down there on the bottom. There's not much I can do about that, I'm afraid. But yeah, this is pretty good. Okay, now I'm back on the field tech. want to see if I can clean up that ringing a little bit. Hopefully not impact the slew rate too much. First I'll try the 47 pico, and yeah, pretty much nothing. It is lower impedance. Let's try, I'm going to jump up here to a 330 picofarad. Put that on there. Oh yeah, that cleaned it up. It cost us some slew rate. Let me back off then. Find a 100 picofarad cap. Where are you? Ah, here's one. 100 pico. Yeah, that's better. It's not ideal, but still a ringing on the bottom, but it clears up the top. So maybe a 220 pico would be better. I don't know if I have one. A 330 definitely cleans it up, but it slows our signal down. I mean, it's still plenty fast enough, I think, for testing with the amplifier. So there you have it, the Field Tech and the microcontroller, or should I say the Field Tech. Actually not as bad as I expected. I mean, for a around $60 arbitrary waveform generator, and it does do a half decent job with the square waves. Microcontroller for being, you know, those are what, $3 chips. I mean, when you get them programmed. If I bought these chips, you know, just bare chips and programmed them myself, you know, those chips are pennies on the dollar. So, you know, that's also a very viable solution for generating fast square waves. So in the next video, I'll carry on with testing the amplifier. Thanks for watching.